So I just wanted to go over solutions to some of the example problems in the textbook, Investigating Physics on page 90. If you don't have textbooks with you, the photo of the problem page is in the description. So then, for question number 1, I want to calculate the maximum potential energy that pole vaulter Sergei Bubka has as he jumps over the pole. Take a look at this though. When Sergei jumps, so this is my diagram of the pole vaulter, he jumps over the pole. He's some height above the pole, and to calculate the maximum potential energy, we need to find the height at which the center of gravity of the vaulter is. We know that height is 30 centimeters above the height at which the pole is suspended, and we know also that that height is 6.14. So the total height is equal to 6.14 plus 0.3, and that's 6.44 meters. So to calculate potential energy, we simply apply our potential energy formula. This is an important formula that we need to remember. That's equal to mass times acceleration due to gravity times the height, and in this case we get mass is 80 kilograms times 9.8, and all that times height, which is 6.44, and the total energy ends up being 5048.96 joules. Then in problem number 2 on the same page, we have a Boeing that's taking off a runway, and we're asked to calculate its kinetic energy. We know mass is equal to 360,000 kilograms. We know that the final speed is equal to 80 meters per second. So we can calculate the kinetic energy using the formula mv squared over 2. Another very important formula to remember for those problems. And that's equal to 3,612,34 times 80 squared, all divided by 2. So the final value for this problem will be equal to 1.152 times 10 to the power of 9 joules. Third example that I wanted to cover here is question number 3. Question number 3 is a little bit more involved, and it actually involves the principle of energy conservation that we spoke about today. So in this question, we're looking at a gymnast who's suspended from a ceiling on a rope, and that rope this is the rope. Rope length is 4 meters, and the gymnast is suspended over here. Now the gymnast is swinging left and right, and at its highest position, let's say that this position is somewhere over here. At its highest position, just draw it a little bit better. At its highest position, the gymnast is 1.5 meters away from the ceiling, which means that the gymnast position from the bottom, let's say, of a journey from the rest position at the bottom of the length of the swing is 2.5 meters. Okay, so when gymnast swings, we can think about it as a pendulum. So in any kind of pendulum, you can talk about a situation where the pendulum is either at the start of its motion, at the bottom of its motion over here, or at the end of its swing over here. So when the pendulum starts, it doesn't have any kinetic energy, it only has potential energy. So let's write this down as EP1 equals to some value mgh, and kinetic energy will be equal to 0. Then as the pendulum swings, the potential energy decreases and the kinetic energy increases. So the height in this case, remember that this is our height for the calculations of the potential energy. That's the height. So kinetic energy will be equal to 0. As the pendulum drops the full height, so it drops this distance. It's at the bottom of its swing, and it has its highest speed. We can say that kinetic energy is equal to mv squared over 2, but the potential energy can be said to be 0 because the pendulum dropped its all height. And then the pendulum swings back again, going this direction. So its potential energy comes back to be equal to mgh. And kinetic energy will be equal to 0 again. So for this gymnast, what I want to do is I'm going to denote the potential energy at the top of the swing over here. I'm going to call it EP1, and I'm going to call the kinetic energy as EK1 as well. This is a 1. The tablet didn't pick it up. At the bottom of the swing, I'm going to say that kinetic energy is denoted with EK2 and potential energy will be EP2. What we need to remember is that sum of kinetic and potential energies at the top and at the bottom of the swing doesn't change. So potential plus kinetic at the top of the swing is equal to potential plus kinetic at the bottom of the swing. So what we can rewrite it as, at the top of the swing, there is no speed, so the kinetic energy is equal to 0. And at the top of the swing, the potential energy is expressed as mgh, where m is the mass of the gymnast, g acceleration to gravity, height from the bottom position. So this would be this distance here. That would be my height. Now, at the bottom of the swing, kinetic energy has some value, but the potential energy is equal to 0, and kinetic energy, we can say that it's mv squared over 2. So this is my expression for the conservation of mechanical energy at the bottom of the swing. Potential plus kinetic at the bottom is potential plus kinetic at the top. Now, if I rewrite it, getting rid of the zeros, zeros are unnecessary here at all, so let me just rewrite this without zeros. We have mgh is equal to mv squared over 2. Now take a look at this. Mass is a common factor on both sides of my expression, so I can get rid of mass. And I end up with a situation where if I multiply across by 2, I get v squared is equal to 2 times g times h. Now, to find the value of v, I simply take a square root of both sides. So v is equal to square root of 2 g h. So now I have the formula for v, and I can substitute values into my formula. Let's see. I have to. G is obviously acceleration due to gravity. Eraser 2 times 10, 2 times 9.8 times. Now the height, as we mentioned previously, it's important that we recognize what the height is. The height is the distance between the top position in this motion and the bottom position in this motion. It's the height at which the potential energy is calculated. So that's the mgh. And that height is 1.5 meters from the ceiling. So it's 2.5 meters from the bottom of the swing. So that's why I put in 2.5 into the question. 2.5. And if we calculate that, we'll find the speed is equal to 7 meters per second. Okay. Now in the next part of the video, I'm going to give you some pointers on how to approach the questions from homework. Part of the video, I just wanted to talk quickly about the homework problems. So for homework, question 1 and question 2 simply will be an application of the calculations involving potential energy, EP equal to mgh. And you can transform that equation to find the values you're looking for. And if you have any questions about how to do that, you can raise them tomorrow. Then for question 3, 4, and question 5, we're much more concerned with principle of conservation of mechanical energy. And let me just go over this fairly quickly again. Let's imagine that we're throwing an object from a height h. this is our object, and this is our height h over here, from here to here. At the beginning of a motion, the object will have some potential energy, let's call it EP1, and will have some kinetic energy. If it's not moving, obviously that kinetic energy will be equal to 0. Somewhere along its motion, it will have a different potential energy, and because it's falling down, this potential energy is decreasing, and the kinetic energy, let's call it 2 actually, and the kinetic energy is going to increase, is going to change a little bit. And finally, at the final stage of the motion, where the object is very close to its maximum speed, again we'll have some potential energy, and it will have some kinetic energy. As the object is moving from the maximum height to its minimum height, the potential energy will be decreasing. So at this height, the potential energy is maximum. At this height, potential energy is minimum, very close to 0 or 0. And somewhere along its motion, the potential energy and the kinetic energy will have values that are non-zero. Now, it's important to remember, this is the principle of conservation of mechanical energy, and what we need to apply to these problems, that anywhere along its motion, EP, potential energy, plus kinetic energy 1 is always equal to sum of potential and kinetic energy along its motion. So I'll just put EK3 plus EP3. Now we can substitute the formulas. For potential energy, the important factor is the height along its motion. So that's mgh, let's say 1, plus, for kinetic energy, the important factor is the speed, mv1 squared over 2. That will be equal to, obviously, kinetic energy, but it's first in here, so we'll write it first again, mv. Now speed changed, so we'll change the speed to v2 plus mgh, actually 3 in this case, not 2, because we're looking at the bottom of our motion, mgh3. So question 3, question 4, and question 5 are asking you explicitly to apply those equations to calculate either speeds or velocities and so on. For question number 6, question number 6, question number 7, question number 6 and question number 7, we're looking at a pendulum, and I just want to point out in here that for pendulum, this is our pendulum, and this line, let me redraw this line. So pendulum is suspended from somewhere, and this is the line of the pendulum when it's at rest, when it's just hanging. So this would be the line, but the pendulum swings from some position over here. So in this position, the pendulum is at rest, and you'll note in one of the problems that you have this diagram where that distance here is denoted as height. So this is the height from which pendulum drops, and as pendulum is moving at this position over here, the pendulum has potential energy equal to mgh. Now, as the pendulum swings through its motion at this position, the pendulum will convert all of its potential energy to kinetic energy. So at this position, we'll have kinetic energy equal to mv squared over 2. And again, the pendulum will continue to move along its motion until it reaches its opposite side over here, where again the potential energy will reach its maximum and the kinetic energy will go down to 0. So these questions are essentially asking you to solve that type of situation with the pendulum. Now, question number 7 is slight complication, because what you need to recognize in this case is that we need to apply trigonometric functions to calculate that distance h. Take a look at this. You're given an angle theta of 40 degrees over here, and remember that the length of this distance, so this distance over here, let me maybe rewrite it, the length of this distance over the length of the pendulum. So this is the length of the pendulum, and let's call this distance A. take a look at this. Distance A over L is the same as cos in this case actually, cos of my angle theta. So we can use that formula to find the distance, the length of distance L, and you can use that distance L to calculate your height, because height is equal to length of the pendulum minus A. So we can use this to find the solution to the third problem. Okay, and in the final two problems, we're looking at a combination of two principles of conservation. So we're looking at the principle of conservation of momentum, mv1. Actually, let me just rewrite this properly. So initial speed for two objects, mu1 plus m2 u2 is equal to m1 v1 plus m2 v2. So we can use the principle of conservation of momentum to find speed before and after the collision, and you can use then the final speed to find the kinetic energy. And that's it. See how you get on with those problems. If you have any questions about this, let me know. And if you have any comments about this video, also let me know in the class tomorrow. So thanks for your attention.